Hello everybody, I'm Supreet and here to present our work on index-based trading in cloud spot markets. This is joint work with my advisor David Irwin. Okay, so we begin today with a cloud proverb. Idle cloud is provider's workshop. I'm going to use a couple of numbers to set a context for this, and believe me, I mean it in a most positive way. As cloud has rapidly expanded over the last few years, cloud providers have responded gleefully by scaling up their infrastructure. Right? While this is all very positive, they face an important hurdle. The large data centers have dismal utilization levels. In their seminar lecture notes, Barroso and Hosel of Google put it at 10 to 50%, which is not economically sustainable. Right? So now providers are responding to this by turning the infrastructure cloud, which kind of started as a simple per hour rental service, into a full-fledged marketplace. For example, Amazon EC2 sells 76 different hardware configurations, each of which is available under 8 different contracts, right? That vary in the pricing model, time commitment, the performance guarantees, and the risk exposure. The clearest example of this trend is the spot market, which is going to be the focus of our talk today. Okay, in simple terms, these are transient servers that come with no availability guarantees. Amazon uses a market mechanism to sell them. The users first bid for servers in a second price auction. Amazon continuously evaluates the supply demand balance and prices the servers appropriately. If a user's bid is above the spot price, they're allocated the server. And when the spot price goes above the user's bid, Amazon reserves the right to take back the server with a 2-minute warning. So if this makes you think that Amazon has hired a bunch of economists and run a little experiment, we are completely off. Okay, so to get a sense of how big the spot market is, so just last year, Amazon announced that the total compute capacity consumed on the spot markets in 2016 is more than the total compute capacity that was consumed across all of EC2 in 2012. Right? So why are folks using the servers which could be taken away anytime? Because they're very cheap. So obviously the system community also has taken a deep interest in making these less reliable servers more reliable for applications. Right? A core aspect of that research is the spot price prediction. So why is this critical? To understand this, let's look at a spot price trace from an example server over a month. It's characterized by low price levels interspersed with unexpected price spikes, right? So let's say a user has bid and acquired this server at the indicated price. That's the dotted line there. While this is an excellent bid for the first 15 days of the month, the user will experience many revocations in the latter part, which directly affects the application performance. So thus, a good prediction lets us do two important things. One, it lets us reduce revocations by bidding correctly. And second, it lets us compare potential savings across different servers. So as a result, many researchers and practitioners are taking a deep interest in tackling this problem. Right? So this big list here is a sampling of this work that's gone in this direction in the just last 2 years. Okay, so these include predicting prices based on the time series analysis of the historical price traces, to predicting prices for a specific type of application like MapReduce, right? It's not only an active research area, but a lot of tensions flare here. For example, a paper titled How to Bid the Cloud in 2015 was responded to with another one titled How Not to Bid the Cloud in 2016. Anyway, I digress. Okay, so you might be wondering, why aren't things hunky-dory, right? So while price prediction is possible, predicting these accurately is difficult. Right? To understand this, we should look at the scale of the EC2 spot markets. Right? Amazon has about 68 different hardware configurations available in the spot market, each of which come with either Windows or Linux, and will be housed in one of the 2 to 5 data centers or zones that exist in each of the 14 worldwide regions. Amazon prices each combination of this by itself. Right? So thus we arrive at a staggering number of 7,600 spot markets. To put that in some perspective, the New York Stock Exchange has less than 3,000 publicly traded stocks. Okay, so why does Amazon sell each combination in a separate marketplace? Quite likely the reason is that the supply-demand dynamics are very local to the particular server they're selling and where it's hosted, in which data center it's hosted. But anyway, whatever the reason, right, this structure poses three significant challenges for price prediction schemes. First, it's unlikely that a one-size-fits-all grand prediction model even exists. Second, while we understand how to interface with the spot markets, we have no visibility into the internals of how it's priced. Not only that, Amazon has a high leverage because they are both the producer and the consumer in this scenario, right? And finally, unlike say electricity spot markets, which partially correlates with weather or temperature metrics, the way the spot servers are consumed has very little correlation with any external variables. So all prediction schemes are left with is just the past price history to make predictions, right? So if this makes you think, aren't some of these challenges faced by other people, like maybe investors in financial markets? Yes, you're spot on. Obviously, our friend Jim Cramer makes predictions on individual stocks, and so are most investors. But their decisions are guided, at least in part, by broad market-based indices. The S&P 500, for example, gives an idea of how the overall US economy is going. If you like to dig deeper into, say, energy, you would look at S&P 500 energy, or if you want to look into China, you would look at S&P China, right? So in this work, we extend this approach to cloud markets and hypothesize that cloud users are better off making their investment decisions, at least in part, based on the market indices, rather than exclusively focusing on predicting individual servers. Okay, first things first, how do we define a cloud index? So as we all know, an index is a collective measure of a group of items, right? So there are two parts to calculating the cloud index. First, we need to characterize the individual servers and then combine them to arrive at a numerical index value. Okay, so to characterize an individual server, this is straightforward. We're taking the ratio of its price, that's Pi, to that of the resources it represents, right? So for a cloud server, this is primarily the compute capacity indicated in Ci and the memory, which is Mi. We have combined those two using a geometric mean. So once we normalize the individual servers, we combine them by taking an arithmetic average of the group of servers, right? So now we have a sense of how we compute the market index. Let's apply it to a few markets. So we start with the global view of the markets. But even before we get to the global spot markets, let's apply this index formulation to on-demand markets. Yes, on-demand prices don't vary across time, but they differ across regions. So on the x-axis, the graph here shows 14 different regions, and the y-axis is the index value corresponding to a particular region. So we see that the average price per resource varies significantly along the regional boundaries. For example, the compute capacity is 50% more expensive in Brazil than in Canada. Okay, now we look at the corresponding. We will look at the corresponding regional graphs in the next slide. But let's first look at the worldwide spot market as a whole. So the graph here on the x-axis shows the time, and the y-axis is the cumulative index value for all of 2,800 Linux spot markets worldwide. Okay, so two significant things stand out. First, at the global level, the spot markets are remarkably stable, right? And second, they're priced at about 80% of the discount from the average on-demand price. So now we've looked at the global markets. Let's dig a bit deeper into other granularities. Okay, so shown here is the same worldwide global spot market from the previous slide. If I consider only one region in it, say US East 1, this is how it would look like, right? Let's go down another level into one of the availability zones in the US East 1, which is US East 1A. That looks like this. Finally, I'm going to show a particular server chosen in this region. Okay, so I want to make a couple of points here. First, as we increase the market granularity clockwise from top, we begin to see more features in the index level, right? So at the extremes, the worldwide market shows no spike, and the other extreme, the individual market, is filled with the characteristic spike of the spot market. So this brings me to my second point, which is price predictions are much easier and more accurate at higher market levels than individual server levels. So while this is obvious in hindsight, It's a nifty insight with many applications, right? So in the next few set of slides, I'm going to illustrate one of the applications that we call server trading. Okay, let's consider a flexible application, right? By flexible, we mean an application that's either virtualized or containerized, that's capable of consuming the resources of the underlying server and doesn't have strict geographical constraints. Right? There are many examples of such flexible jobs. A batch interactive job running on Spark framework, or a legacy financial application which say processes streaming data from worldwide stock markets continuously, etc. Right? So we argue that such applications can benefit from server trading, though we are not the first one to say that. Many reasons, some obvious, some not. Spot markets are dynamic, which means that the best server for a given application keeps on changing. Spot markets also provide many arbitrage opportunities, especially since not all applications and users are flexible enough to benefit from price inversions. Finally, unlike many other markets, there's always a buyer if you want to get rid of your server. So the provider always takes back the server, right? But like all good things in life, it's not really free. So each server trade incurs a transaction cost, right? This could be in the form of the time and resource spent to migrate the disk and memory state of the application, or the overhead of the fault tolerance mechanism, which is needed to make the application successfully move from one server to another, or the unused portion of the minimum time slice that the provider charges for your server. So our goal here is to demonstrate the effectiveness of the market-based indices in performing server trades that are cost efficient. But before we do the actual trading, let's cover a couple of building blocks. Okay, so the first thing is to define what is the best server, right, at a given time for a given application, of course. So while there are many techniques that are possible, we use Sharpe ratio. This is commonly used in finance to understand the risk-reward trade-off. So in the formula here, the numerator captures the expected benefit of using a spot server as compared to an on-demand server, which is a risk-free server, right? And the denominator represents the volatility risk associated with using a spot server. So in essence, we choose a server that's not only got a low price but also got low volatility. So once we know how to pick a best server, the next question is where, right? So the figure here shows the scope of trading that's possible and easy to spot markets. So the blue boxes here correspond to what Amazon calls the regions, and the red dots are the data centers or the zones that lie within a specific region. So at a given point of time, a server resides in one of these red dots. So moving to another server within a red dot incurs the lowest transaction cost among all the migrations. And the next one, which is moving across dots that belong to same blue box, incurs additional cost. But moving across the blue boxes incurs the most overhead. We will shortly quantify this in the next set of slides. Okay, so with this background, we are ready to define our trading policies. So the policies differ along the three metrics that we just now discussed: how to choose a server, how does it allow trading, and if so, where, and what's the transaction cost that the trading incurs. The first policy here, it simply picks the globally best server at the start time and then allows no trading at all. So it got no transaction cost. The second one, again, picks the globally best server, but allows trading within the zone in which we have picked the server. So basically, you're committing to a zone. The rationale is that the transaction costs within the zone are minimal, essentially a fixed cost of the order of a few tens of seconds. So, and the third one is same as the first two, but it allows global trading. So this is an extreme case because global trading incurs a cost that's proportional to the amount of data that's being moved, right? Which will be of the order of minutes to hours. The rationale here, however, is that the best server at a given time may not be in the zone that you picked, so thus it makes sense to move. As you can see, all these three policies pick individual servers, right? For the final one, which we call the index-based trading, we first compare the indices of all the zones in the world, and then we pick the best zone. Once we decide on the best zone, we pick the best server within that zone and allow trading only within that zone. So it's sort of a middle ground between, you can see, policies 2 and 3. Okay, now to evaluate these policies, we simulate running a long-running flexible application on EC2 over a period of a month. So we want to evaluate these policies along two aspects. First, how much did it cost? And second, how available was the application over the course of this time? So the graph here shows the policies along the x-axis and the cost along the y-axis, right? So we have normalized this to the maximum cost, which happens to be the policy that doesn't trade, which is indicated in gray. So while that's the worst case, the best is achieved by the global trading policy, which is the blue one, costing only about 20% of the maximum. So this indicates that the best market continuously changes and one needs to move worldwide to benefit from it. However, the next graph shows the downside of global trading. So this is the availability graph with the policies along the x-axis and the availability, the number of nines of availability along the y-axis. So it's obviously not to the scale. The first thing we notice is that the global trading policy, which is in blue, achieves the worst availability, just a single nine. So this is because of the high cost incurred in moving globally. It'll have a downtime basically, right? But rather surprisingly, the no trade policy also doesn't perform well, likely indicating that there's enough market volatility to make some form of migration attractive to not migrating at all, right? But in summary, when we look at these two graphs holistically, we see that the index based trading, which is in green, achieves best of the both worlds. It costs less than 40% of the maximum cost, and it got the second best availability, right? So with that, I rest my case and I briefly conclude our discussion. Spot price spot price prediction is an active area of research. We highlight the importance of using broad market-based indices to make decisions as opposed to the current practice of predicting individual server behavior. Next, we demonstrated the effectiveness of cloud indices by using them to perform server trading for flexible applications in a cost-efficient way. In terms of future work, we are excited about what we call the application-specific indices and also using cloud indices to develop a benchmark to compare multiple spot-based systems. With that, I thank you for your patience and would be happy to discuss anything about this work. Thanks.